Welcome to my sleep science channel. Like, subscribe, and tell me where you're watching from. Tonight we are going to drift into one of the quietest and most unsettling questions in cosmology. If the universe is expanding, what exactly is it expanding into? To begin gently, we need to ground ourselves in something real and observable. When astronomers say the universe is expanding, they are not describing galaxies flying outward into empty space like fragments from an explosion. They are describing something more subtle and more difficult to imagine. The distances between distant galaxies are increasing over time, not because those galaxies are moving through a pre-existing empty arena, but because the very space between them is stretching. This idea becomes clearer when we think about a simple analogy. Although no analogy is perfect, imagine the surface of a balloon being slowly inflated. Tiny dots on the surface represent galaxies. As the balloon expands, every dot moves away from every other dot. Yet none of the dots is actually traveling across the surface. The surface itself is expanding. If you were a two-dimensional creature living on that surface, you would not experience a center of expansion. Every direction would look like it is moving away from you equally. In the same way, our universe does not appear to have a center from which everything expands. Every galaxy observes other galaxies moving away. The farther they are, the faster they appear to recede. This is not because those galaxies are firing through space like projectiles, but because space itself carries them apart. This leads us into a strange but important realization. When we ask what the universe is expanding into, we are already assuming something that may not be true, that there exists an external container, a larger empty space surrounding our universe, into which it grows. However, in modern cosmology, space is not considered a substance inside a larger room. Space is the room itself. It is not located inside anything else in the same way objects are. So when we say expansion is happening, we are not pointing outward into a surrounding void. We are describing a change in the geometry of the universe itself. Distances become larger because the metric, the rule that defines distance, is evolving over time. Still, the human mind resists this idea because everything in our daily experience expands into something. Smoke rises into air, rivers flow into seas, explosions expand into space. So it feels natural to ask, what is outside the universe that allows it to grow? At this point, modern physics gives a very quiet answer. The universe does not require an outside in order to expand. Expansion is not movement into emptiness, but a transformation of all existing spatial relationships at once. Every region participates in the change simultaneously. As we continue exploring this idea, we will move slowly from what we can observe to what we can infer, and finally, toward the edges of what may never be directly answered. For now, the key idea to hold gently in mind is this: the universe is not expanding into space. It is expanding space itself. And in the stillness of that thought, we begin to see why the question feels so natural. And yet, why the answer leads us away from intuition and into something far more subtle. In everyday thinking, expansion usually means something simple and familiar. A gas spreads out inside a room, smoke disperses into the air, an explosion pushes fragments outward into empty surroundings. All of these examples share a hidden assumption that there is already a space waiting to receive the expansion, and that the expanding thing is moving through it. In cosmology, that assumption quietly breaks. When scientists talk about the expansion of the universe, they are not describing motion through space in the usual sense. They are describing a change in the structure of space itself. This distinction is subtle at first, but it becomes the key to understanding everything that follows. To picture this, imagine space not as a static stage where events happen, but as something more like a woven fabric. Not a fabric in a physical, touchable sense, but a mathematical one, where distances are defined by relationships rather than rigid rulers. In this view, what changes over time is not just where objects are, but the rules that determine how far apart they are. So when we say the universe is expanding, we are saying that the distance rule is stretching. 2 points that are not gravitationally bound, such as distant galaxy clusters, will find that the space between them grows larger, even if neither is actively moving through a background. This leads to a counterintuitive, but important realization. Expansion is not something happening at a single location. It is happening everywhere at once. Every region of the universe participates in it, except where local forces are strong enough to resist it. At small scales, atoms, planets, solar systems, and galaxies remain stable because electromagnetic and gravitational forces dominate. But at the largest scales, where gravity is weak across vast distances, space itself becomes the dominant factor. One of the most important consequences of this is that there is no edge being pushed outward. If the universe is all of space that exists, then expansion does not require a boundary moving into an outside region. There is no leading front of expansion, no wall separating expanded and not yet expanded regions. Instead, the entire spatial structure evolves together. This is where intuition struggles most. The mind tries to imagine the universe as a thing inside something larger, but in modern cosmology, the universe is not a thing inside space. It is space, along with everything within it, including time, energy, matter, and the laws that describe them. To understand expansion more gently, we can think about embedded coordinates. Imagine a grid drawn on a rubber sheet. If the sheet is stretched, the grid lines move apart. From the perspective of any point on the grid, it appears as if everything else is moving away, yet nothing is actually traveling across the sheet in the traditional sense. The sheet itself is changing. In cosmology, galaxies act like those grid points. They are not the cause of expansion, and they are not being pushed by a force in the usual sense. They are simply embedded in a geometry that changes over time. There is also a deeper layer to this idea. The expansion of the universe is described mathematically by solutions to Einstein's equations of general relativity. These equations do not describe space as a passive container. Instead, they describe space-time as a dynamic entity that responds to energy, matter, and pressure. In certain solutions, the natural behavior of space-time is to expand. This means expansion is not an added feature. It is one of the possible states of space-time itself, like a surface that can remain flat, curve, or stretch depending on its contents. When we observe distant galaxies, what we actually see is evidence of this stretching. Light traveling through expanding space gets stretched as well, increasing its wavelength. This is part of why distant galaxies appear redshifted, a phenomenon that quietly reveals the ongoing growth of spatial separation over cosmic time. Yet even with these observations, the mind returns to the same question. If space is expanding, what is it expanding into? At this stage, cosmology gently redirects the question. Expansion does not require an external space because space is not treated as an object inside a higher dimensional container. Instead, space is the totality of spatial relations itself. Asking what lies outside it may be similar to asking what is north of the North Pole. The question assumes a direction that stops being defined at the boundary. So the idea of expansion becomes less about outward movement and more about internal change. The universe does not grow into something else. It changes its own scale, everywhere, all at once. And as this thought settles, it begins to feel less like an image and more like a shift in perspective, where the universe is not a place inside a larger emptiness, but the total stage in which even the concept of outside has no defined meaning. To move deeper into this idea, we have to slow the mind down and separate two concepts that often get blended together in everyday thinking: One is the idea of objects existing in space, and the other is space itself as something that exists independently, like a container. In daily life, it is almost impossible to separate them, because everything we interact with is already inside space, and space feels like an invisible background that simply is there. But in modern cosmology, space is not treated as a background at all. It is treated as part of the physical reality that can change, stretch, curve, and evolve. When physicists describe space, they are not describing a substance like air or water. They are describing a structure defined by relationships. Distance is not a fixed thing stored in a cosmic warehouse. It is a property that emerges from how points in the universe relate to each other. This is why the phrase, fabric of space, is often used, even though it is only a metaphor. It helps the mind imagine that space has internal structure, something that can be stretched or compressed without needing an external environment. Now comes the important shift. If space can stretch, then that stretching does not require space to be inside something else. The stretching is itself the change. There is no second layer outside it where the change is taking place. The geometry of the universe is the full system. To understand why inside something is not required, we can think carefully about what inside means. Inside always requires a reference container. A cup is inside a room is inside a building is inside a city. But this chain depends on always having a larger space that contains the previous one. If we extend that logic to the universe, we quickly reach a point where the concept loses its grounding. If the universe is everything that exists in terms of space and time, then there is no larger spatial container left to place it in. The idea of outside the universe becomes undefined, not because it is hidden, but because the structure needed to define it is missing. This is where general relativity reshapes intuition in a quiet but profound way. In Einstein's description, space and time are not separate from physical reality. They are part of a unified structure called spacetime. This structure is not fixed. It responds to energy and matter. It can bend near massive objects, and it can expand on cosmic scales. In this framework, asking what space is inside is similar to asking what a shape is drawn on before the shape exists. A circle drawn on a sheet does not require the sheet to exist inside something else for the circle to be meaningful. The geometry is self-contained within its own definition. Still, the mind resists because everyday experience constantly reinforces the idea of containers. Even our imagination often defaults to picturing the universe as a bubble sitting in a larger emptiness. But that image quietly imports an assumption that physics does not require. The universe, as described by current cosmology, does not need an external stage. It is not an object placed in a bigger arena. It is the arena itself, along with everything that can happen within it. This also changes how we think about motion. In a container-based universe, motion is always relative to the background space. But if space itself is dynamic, then motion can also be described as changes in the geometry that defines distance. Two galaxies can appear to move apart without either of them traveling through a fixed medium. This is not just philosophical. It is measurable. The expansion of space affects the wavelength of light traveling through it. As space stretches, the light stretches too. This is observed as redshift, a systematic shift toward longer wavelengths in light coming from distant galaxies. So in a very real sense, space is not just an abstract idea. It has observable consequences. It interacts with light, with distance, and with time in ways that can be measured across billions of years. Yet even with these measurements, the question returns in a softer form. If space is all there is in terms of spatial structure, then what is it in at all? At this point, physics does not offer a hidden room behind reality. Instead, It gently steps back and says that the question assumes a framework that may not exist. In requires an external space. And if no such external space is defined, then the question cannot be completed in the usual way. So the fabric of space is not suspended inside something larger. It is not floating in a cosmic ocean. It is the definition of spatial relationships themselves, unfolding over time. And as this idea settles, it begins to feel less like an object we are trying to picture, and more like a boundary of imagination itself, where language starts to stretch beyond what everyday experience was designed to describe. When people first hear about the Big Bang, the most natural image that appears in the mind is an explosion. Something extremely dense, packed into a tiny point, suddenly bursting outward into empty space. That image is powerful, and it comes from familiar experiences like fireworks or detonations. But in cosmology, that picture is not quite right, and it quietly leads the imagination in the wrong direction. The Big Bang was not an explosion inside space. It was an expansion of space itself. This difference changes everything about how we understand the origin of the universe. In an explosion, matter moves outward through an already existing environment. There is a center, a surrounding emptiness, and fragments traveling through that emptiness. But in the early universe, space and time themselves were part of the process. There was no pre-existing empty room for the universe to expand into. Instead, what we call the Big Bang refers to a state where the universe was extremely hot, extremely dense, and extremely small in terms of spatial separation, and then began to expand as space itself evolved. To understand this more gently, imagine reversing time in your mind. Galaxies are currently moving apart. If you rewind that motion, they come closer together. Rewind further, and the universe becomes denser and hotter. Keep going back, and distances shrink toward extremely small scales. But at no point in this process do we need to imagine a center point in space where everything started exploding outward. Every region of space was involved in the same process. This is one of the most subtle but important insights in cosmology. The Big Bang did not happen at a location. It happened everywhere at once. In the early stages of the universe, space itself was dramatically different. The distances between points were shrinking as we moved backward in time. But those points were not located in a surrounding emptiness. The entire geometry of space was in a different state, much like a stretched fabric that can be compressed back into a tighter configuration. As time moves forward from that early state, the fabric relaxes and expands. The expansion is not a motion through something, but a change in the scale of spatial relationships. There is also a common misunderstanding that the Big Bang was the moment the universe came into existence from nothing. In modern cosmology, the Big Bang describes the earliest state we can meaningfully model using current physics, not necessarily the absolute beginning of existence itself. The equations that describe the universe break down when we push them all the way to the initial singularity, which suggests that our current understanding is incomplete at extremely early times. What we can say with confidence is that the universe has been expanding from a hot, dense, early phase, and that expansion continues today. This expansion is not uniform in the sense of objects flying outward. It is uniform in the sense that space itself stretches everywhere. Any two sufficiently distant galaxies will see their separation increase over time, not because they are moving through space, but because the space between them is increasing. This leads to another important idea. If expansion is a property of space itself, then even during the earliest moments, there was no external space waiting to receive the universe. The universe was not filling a void. It was defining the structure of space and time as it evolved. In this view, asking what the universe expanded into at the moment of the Big Bang is like asking what direction a ruler extends in before there is any space defined for directions at all. The concept of outside relies on spatial relationships that are already established. This is why cosmologists often say that the Big Bang happened everywhere. It is not a poetic phrase. It reflects the fact that every point in space shares the same origin in time when traced backward through expansion. Still, the human mind naturally tries to imagine a boundary, a starting point, or a central explosion. But the more accurately we describe the universe, the more those images begin to dissolve. What remains is a universe where distance itself is dynamic, and where time carries space from one state to another. As we sit with this idea, the early universe becomes less like a burst of matter into emptiness, and more like a shift in the very rules that define separation, distance, and geometry. And in that shift, the Big Bang is not an explosion in space, but the beginning of space behaving in a way that allows expansion to exist at all. From our small position inside the universe, most of what we know about cosmic expansion does not come from direct experience, but from careful observation of light that has traveled for billions of years. Everything we understand about the large-scale behavior of space is built from signals that arrive slowly, quietly, and stretched across unimaginable distances. The universe does not show us its structure directly. It shows us its history. When astronomers look at distant galaxies, they are not seeing those galaxies as they are now. They are seeing them as they were when the light left them. Because light travels at a finite speed, every observation is also an observation of the past. The farther away something is, the deeper into cosmic history we are looking. This is one of the most important reasons we can study expansion at all. We are not watching space stretch in real time like a slow-motion film. We are comparing different layers of time embedded in light arriving from different distances. One of the clearest signs of expansion is redshift. When light travels through expanding space, its wavelength is stretched along with the expansion itself. This makes the light shift toward the red end of the spectrum. The more distant a galaxy is, the more its light is shifted, which tells us that space has expanded more during the journey of that light. This is not a small effect. It is a consistent pattern across the observable universe. Galaxies that are farther away are not only dimmer, but also more strongly red-shifted. This relationship is what led to the discovery that the universe is expanding in the first place. What makes this even more interesting is that the expansion is not just something we see in one direction. No matter where we look in the sky, distant galaxies appear to be moving away from us. This creates a very important conclusion. We are not at the center of expansion. Every observer, anywhere in the universe, would see the same general pattern type. This leads to a deeper realization. The universe does not have a privileged viewpoint. There is no special location where expansion begins or appears strongest. The laws of physics operate the same way everywhere, and expansion appears uniform on very large scales. When we map galaxies across space, we find that they are not evenly spread like points in empty space. They are arranged in a vast cosmic web. Filaments of galaxies, separated by enormous voids, stretch across the universe in a complex structure shaped by gravity and expansion, working together over billions of years. Even though space is expanding, local structures remain bound. Galaxies do not fall apart because gravity holds them together more strongly than expansion can separate them. Solar systems, planets, and atoms are even more tightly bound. This is why expansion is only noticeable at the largest scales. So from Earth, we see a layered universe. At small scales, everything feels stable and fixed. At larger scales, galaxies drift apart. At the largest scales of all, space itself reveals its stretching nature through the patterns of light we receive. Another important observation comes from the cosmic microwave background. This is a faint glow of radiation that fills the entire universe, coming from a time when the universe was much younger and hotter. It is like a snapshot of the universe when it first became transparent to light. The uniformity of this background radiation tells us that the early universe was extremely smooth, and that structure formed gradually over time as expansion continued. When we combine redshift data, galaxy distribution, and cosmic background radiation, we build a consistent picture. The universe is expanding, and that expansion is not random. It follows precise physical laws that can be measured and predicted. Yet even with all this evidence, we still only observe the universe from one perspective, our own. We cannot step outside it to compare it with anything else. Every measurement is made from within the expanding system itself. This is why cosmology is sometimes described as a science of inference. We do not see the full structure directly. We reconstruct it from the way light and matter behave over time. And as this realization settles, something subtle becomes clear. The universe does not need to show us an outside for us to understand its expansion. It reveals its behavior entirely through internal signals, through light, motion, and time itself. In that quiet way, observation becomes not a window into something external, but a deep reading of the universe's own unfolding history. As we continue moving deeper into the structure of the universe, there is a quiet boundary that appears, not as a physical wall, but as a limit defined by time, distance, and the finite speed of light. This boundary is called the cosmic horizon, and it shapes everything we are able to see, measure, and understand about the universe. The key idea is simple at first. Light takes time to travel. Because of this, the universe we observe is always the universe of the past. When we look at distant galaxies, we are not seeing them as they are now, but as they were when their light began its journey toward us. For nearby objects, the difference is small. For extremely distant ones, the difference becomes enormous. The cosmic horizon is not a physical edge of space. It is the maximum distance from which light has had enough time to reach us since the beginning of the observable universe. Beyond this boundary, there are regions that exist, but their light has not yet reached us, and in some cases, may never reach us due to expansion. This creates a very important distinction. The observable universe is not the entire universe. It is only the portion of the universe from which information has been able to arrive at our position. Everything beyond that is, at least for now, outside our observational reach. As space expands, this horizon itself changes. Some regions that were once observable become harder to see over time, because space between us and those regions stretches faster than light can traverse it. This does not violate the speed of light locally, because nothing is moving through space faster than light. Instead, the space itself between regions is increasing. This leads to a gentle but strange realization. There are galaxies that we can see today whose light is reaching us after traveling for billions of years, but as time continues, the expansion of space may eventually stretch their distance so much that their future light will never reach us again. In a sense, the universe is slowly writing and then hiding its own history from any single point of view. The cosmic horizon is not fixed. It depends on the age of the universe and the rate of expansion. As time passes, new light reaches us from farther regions, while other regions slip beyond reach. This creates a dynamic boundary between what is observable and what is not. To understand this more intuitively, imagine being in a vast ocean at night, surrounded by fog. You can only see the glow of distant lights within a certain radius. Those lights are real, and the ocean extends far beyond them. But your ability to see them depends on how far light has had time to travel through the fog. Now imagine that the fog itself is expanding and stretching. Some lights gradually fade, not because they disappear, but because the fog between you and them becomes too vast for their light to cross. In cosmology, the fog is not dust or obstruction. It is the expansion of space combined with the finite speed of light. There is also a deeper horizon known as the particle horizon. This represents the farthest distance from which any signal could have reached us since the beginning of the universe. It defines the boundary of all possible information we can ever receive about the past of the universe. Beyond this limit, regions may exist that are forever disconnected from our observable history. Even more subtle is the event horizon in cosmology, which relates to the accelerated expansion of the universe. Due to dark energy, some regions are not only out of reach in the past or present, but will remain forever unreachable in the future. Light emitted from those regions now may never overcome the expansion separating us. These horizons remind us that the universe is not fully accessible from any single point. Every observer has their own observable region, shaped by their location and the age of the universe. Another observer in a distant galaxy would have a different observable sphere, centered on them, with overlapping but not identical boundaries. So when we ask what the universe is expanding into, the cosmic horizon adds a subtle layer to the question. It shows that even what we call the universe we can see is only a fraction of a larger whole. But importantly, the horizon is not an edge of space itself. It is an edge of information. The universe does not end at the horizon. Our ability to observe it does. And as this idea settles, it becomes clear that much of cosmology is not about finding boundaries in space, but understanding boundaries in perception. Boundaries shaped by time, light, and the unfolding expansion that quietly stretches everything between distant points into greater separation. One of the most natural ideas the mind forms when thinking about expansion is the idea of a center. If something is expanding, it feels intuitive that there must be a point where it all began, and from which everything is moving outward. In everyday life, explosions always have a center. Ripples in water always start from a disturbance, and smoke always spreads from a source. So it feels almost inevitable to imagine the universe in the same way. But in cosmology, that intuition quietly fails. The universe, as far as current observations and models suggest, does not have a center of expansion. Every point in space sees itself as being surrounded by galaxies moving away in all directions. This is not a trick of perspective in the usual sense. It is a consequence of how space itself expands uniformly on large scales. To understand this, we can imagine again a simplified analogy, not as a literal description, but as a way to soften intuition. Picture the surface of a balloon being inflated. Tiny dots are drawn on the surface. As the balloon expands, every dot moves away from every other dot. Now imagine you are one of those dots. From your point of view, everything else is receding from you. But, importantly, there is no special dot that can be identified as the center on the surface itself. The center of the balloon exists only in a higher dimensional space outside the surface. But in cosmology, the key difference is that there is no confirmed outside space that the universe is embedded in. The universe is not assumed to be a surface inside a larger room. It is the entire spatial structure itself. This is where the concept of a center becomes undefined. A center only makes sense when there is a larger space in which to define positions relative to something external. If space is all that exists in a spatial sense, then there is no external reference frame in which a center could be meaningfully placed. Observations strongly support this absence of a center. When we look in any direction in the sky, we see galaxies receding. The pattern is statistically similar in all directions at large scales. This property is called isotropy, meaning the universe looks the same in every direction when viewed on sufficiently large scales. Combined with homogeneity, the idea that matter is evenly distributed on large scales. This leads to a powerful conclusion. There is no special location in the universe that can be identified as the origin point of expansion. Every observer, regardless of location, will measure a similar large-scale expansion pattern. This can feel counterintuitive because our minds are trained to think in terms of objects moving through space. But in an expanding universe, it is not objects moving away from a center. It is space itself stretching uniformly, increasing the distance between all unbound points. A helpful way to refine this idea is to think about coordinates rather than positions. If space is defined by a coordinate system that is stretching, then the numbers describing distances between points increase over time, even if the points themselves are not moving relative to their local surroundings. The expansion is encoded in the geometry, not in a single directional motion. This is why cosmologists often describe expansion using the scale factor of the universe. The scale factor is a way of measuring how distances between far apart objects change over time. It does not point to a direction or a center. It simply describes how the overall size of spatial relationships evolves. There is also a subtle psychological reason why the idea of a center persists. We naturally place ourselves at the center of our observations because that is where we always experience reality from. When we observe galaxies moving away in all directions, it feels like we are at the center of the expansion. But any other observer in a distant galaxy would see the same pattern from their own position. Every point in the universe can appear to be the center of its own observable expansion. This is not a contradiction. It is a reflection of how expansion works without a privileged location. If we tried to define a global center anyway, we would need an external coordinate system that includes the universe as an object inside something larger. But current physics does not require or define such a system. All meaningful measurements are internal, defined within space-time itself. So the idea of a center dissolves, not because it is hidden, but because the structure of the universe does not support it. And as this realization deepens, the universe begins to feel less like a spreading explosion with a source, and more like a continuously unfolding geometry, where every point participates equally in the same silent expansion, without origin, without edge, and without a privileged starting place. When we picture motion in everyday life, we usually imagine something traveling through a fixed environment. A car moves along a road, a bird flies through air, a stone falls through space toward the ground. In each case, the background is assumed to stay still while objects move across it. But on cosmic scales, that assumption quietly stops working. Galaxies do not primarily move through space in the way cars move through roads. Instead, they are carried apart by the expansion of space itself, while also having smaller, local motions influenced by gravity. To understand this gently, it helps to separate two types of motion that exist at the same time. The first is local motion, which is governed by gravity and other forces. This is the motion of stars orbiting within galaxies, planets orbiting stars, and galaxies interacting in clusters. The second is cosmic expansion, which affects the large-scale distances between galaxies that are not gravitationally bound. These two layers coexist, but they behave very differently. On small scales, gravity dominates. A galaxy like our own Milky Way holds its stars together because gravitational attraction is strong enough to overcome the expansion of space within that region. The same is true for solar systems and even planets. The distances involved are too small for expansion to noticeably affect them. But on extremely large scales, where galaxies are separated by millions of light years, gravity becomes weak compared to the overall stretching of space. In those regions, galaxies appear to recede from each other not because they are actively flying away, but because the space between them is increasing. This creates a subtle but important idea. A galaxy is not like a projectile launched through emptiness. It is more like a point embedded in a stretching coordinate system. The coordinate grid itself is expanding, and the galaxies remain attached to their positions within that grid, even as the distances between them grow. This is why cosmologists sometimes describe galaxies as being at rest in expanding space. That phrase does not mean they are motionless in an absolute sense. It means their motion through space is small compared to the effect of expansion on large-scale distances. A key observational relationship helps reveal this behavior. The farther away a galaxy is, the faster it appears to recede from us. This is known as Hubble's law. It is not that distant galaxies are necessarily moving faster through space, but that there is more expanding space between us and them, leading to a greater increase in separation over time. If we imagine space as a stretching grid, then two nearby points on the grid drift apart slowly, while two very distant points drift apart much faster, because more grid is expanding between them. This effect is not centered on us. Any observer in any galaxy would see the same pattern. From every location in the universe, distant galaxies appear to recede in proportion to their distance. This is a direct consequence of uniform expansion. At the same time, galaxies are not completely passive. They also have peculiar velocities, meaning individual motions caused by local gravitational interactions. For example, galaxies in a cluster can move toward each other and eventually merge, even while the overall expansion of the universe continues on larger scales. So the universe is not a simple uniform flow. It is a combination of local structure and global stretching. Gravity builds structure, while expansion increases separation between structures that are not tightly bound. Over billions of years, this interplay shapes the cosmic web. Filaments of galaxies form along regions where gravity pulls matter together, while vast empty voids expand between them. The result is a universe that is both structured and growing at the same time. There is also a deeper implication hidden in this behavior. If galaxies are carried by expanding space rather than moving through a fixed background, then motion itself becomes dependent on geometry. Velocity is not just change in position through space, but change in the relationship between space and time. This is one of the quiet insights of general relativity. Motion is not separate from the structure of space-time. It is defined within it. So when we look at galaxies drifting apart, we are not seeing a simple outward flight. We are seeing the large-scale expression of a dynamic geometry, where distances are not fixed, but evolve over time. And as this understanding settles, the universe begins to feel less like a collection of objects moving through emptiness, and more like a living structure of relationships, where separation itself is something that changes, stretches, and unfolds across the vastness of cosmic time. At the heart of our confidence that the universe is expanding lies a very quiet messenger: light itself. Light carries information across the universe without needing any fuel or direction once it is emitted, and over vast distances, it becomes a record of everything it has passed through. One of the most important clues embedded in that record is something called redshift. Redshift is not something we see directly in everyday life, but in astronomy, it becomes one of the clearest fingerprints of cosmic expansion. When light is emitted from a distant galaxy, it begins its journey with a certain wavelength, a kind of spacing between the peaks of its wave pattern. As that light travels through expanding space, those wavelengths become stretched, increasing in length. Longer wavelengths correspond to light shifting toward the red end of the visible spectrum. That is why it is called redshift. The farther away a galaxy is, the more its light is shifted, because the light has traveled through more expanding space and experienced more stretching along its path. To understand this gently, imagine light as a repeating pattern moving through a flexible medium. If the medium expands while the pattern is traveling, each wave gets stretched slightly apart from the next. By the time it reaches an observer, the pattern has changed, even though the light itself has not decided to change. The change is imprinted by the changing structure of space. This effect is extremely important because it allows us to measure how fast the universe is expanding at different distances. When astronomers plot the redshift of galaxies against their distance, they find a consistent relationship. The farther a galaxy is, the greater its redshift, and therefore the faster it appears to be receding. This relationship is one of the strongest pieces of evidence that space itself is expanding. It is not based on assumptions or indirect reasoning alone, but on direct measurement of light across the sky. There are different types of redshift, but in cosmology, the most important one is cosmological redshift. This is distinct from redshift caused by motion through space, such as the Doppler effect from a moving object. In cosmological redshift, the stretching comes from the expansion of space itself, not from the object actively moving away through a fixed background. This distinction is subtle, but crucial. If a galaxy were moving through static space, its light would be redshifted due to its velocity. But in the expanding universe, the wavelength increases continuously during the entire journey because the space it travels through is changing as it moves. One of the most striking consequences of redshift is that it allows us to look back in time. Because light takes time to travel, and because its wavelength carries information about how much expansion has occurred since it was emitted, we are effectively seeing different eras of the universe when we observe different distances. Closer galaxies show us a more recent universe. Very distant galaxies show us a much younger universe, when space was smaller and denser. In extreme cases, we are seeing light that began its journey billions of years ago, when the universe was significantly different in structure. Redshift also connects directly to the idea of the expanding fabric of space. If space is stretching uniformly, then any photon traveling through it is carried along that stretching process. The photon does not slow down locally, because locally the speed of light remains constant. Instead, the distance between successive wave peaks increases as space expands. This creates a very important conceptual shift. Light is not simply moving through space like a bullet through air. It is embedded in space-time, and its properties are influenced by the evolution of space-time itself. Because of this, redshift becomes more than just a measurement tool. It becomes a kind of map of cosmic history. Each level of redshift corresponds to a different stage in the expansion of the universe, allowing astronomers to reconstruct how the universe has changed over time. There is also a deeper implication hidden within this. If light carries the signature of expansion, then the universe is constantly communicating its own growth through every photon that reaches us. Every distant galaxy is not just a point in space, but a signal encoded with the story of how space has stretched during its journey. So when we observe redshift across the sky, we are not just seeing galaxies moving away. We are witnessing the dynamic behavior of space itself, written in the language of light. And as this realization settles, the universe becomes less like a static backdrop and more like an ongoing process, where every beam of light is quietly stretched by the unfolding expansion, carrying with it a record of cosmic time that spans billions of years. Light is the closest thing the universe has to a universal storyteller. It does not forget, it does not pause, and once it begins its journey, it carries with it a continuous record of everything it encounters along the way. When we observe the cosmos, we are not seeing it in real time, but through layers of delayed information that arrive after traveling across expanding space. This creates a simple but profound fact. Every observation in astronomy is a form of time travel into the past. When you look at the sun, you are seeing it as it was about 8 minutes ago, because that is how long its light takes to reach Earth. When you look at nearby stars, you are seeing them as they were years ago. When you observe distant galaxies, you are seeing them as they were millions or even billions of years in the past. This delay is not a flaw in observation. It is the only way the universe can be observed at all. Light travels at a finite speed, and because the universe is vast, that speed becomes a natural time bridge between distant regions and our local position. But in an expanding universe, this effect becomes even more interesting because space itself changes during the journey of light. This means that the path light travels is not simply a straight line through a fixed background. It is a path through a stretching geometry. As space expands, the distance between points increases while light is still moving through it. So, the journey of light is always happening in a changing environment. This is why light from very distant galaxies takes not only a long time to reach us, but also arrives altered. Its wavelength has been stretched, its energy reduced, and its original conditions encoded into a signal that we must carefully interpret. In a sense, light is both a messenger and a time capsule. It carries information from a specific moment in cosmic history, preserving it across billions of years of expansion. This leads to an important realization about what we are actually observing when we look into space. We are not seeing a single snapshot of the universe. We are seeing a layered structure of time, where different distances correspond to different epochs of cosmic evolution. Nearby galaxies show a relatively modern universe, with well-formed structures, stable stars, and mature galactic shapes. Farther away, we see younger galaxies, less structured and more chaotic. At the greatest distances, we approach a time when galaxies themselves were just beginning to form. In this way, space becomes a kind of three-dimensional archive, where distance is also depth in time. The farther we look, the further back we go. Now, when we combine this with cosmic expansion, an even deeper layer appears. Because space is stretching, the distance that light travels is not constant over time. A photon emitted billions of years ago may have started its journey in a universe much smaller than the one we see today. During its travel, the universe expanded, stretching both space and the light itself. This means that the universe we observe is not only distant in space, but also continuously shaped by the evolution of space during the journey of light. The past is not simply far away. It is dynamically connected to the present through the structure of space-time. There is also a subtle limitation hidden in this process. We can only ever see as far as light has had time to reach us since the beginning of the observable universe. This creates a natural boundary to our knowledge, not because the universe ends there, but because information beyond that limit has not yet had time to arrive. This is why cosmology is often described as reconstructive science. We do not directly access the universe as a whole. We reconstruct its history from the light that reaches us now, each photon acting as a fragment of a much larger cosmic timeline. Light also connects directly to the expansion question we began with. If space were not expanding, light would still carry information across distance, but it would not be stretched in the same systematic way. The presence of redshift across distant galaxies reveals that light is not just traveling through space, but through an evolving structure of space. So when we study light from the farthest reaches of the universe, we are not just looking outward. We are also looking backward through time, into earlier stages of cosmic expansion, when space itself was in a different state. And as this understanding settles, light begins to feel less like a simple beam traveling through emptiness, and more like a gentle thread connecting every moment of cosmic history, weaving the past and present together through the slow, continuous expansion of the universe. At a certain point, even the most powerful telescopes reach a limit, not because they are insufficiently advanced, but because there's a boundary defined by time itself. Beyond this boundary lies what we call the unobservable universe, a region that may be vastly larger than what we can see, and possibly infinite, yet forever hidden from direct observation. This is not a wall in space. It is a limit in information. The observable universe is defined by how far light has had time to travel since the beginning of cosmic expansion. Anything beyond that distance has not yet had enough time to send its light to us. And because space itself is expanding, some regions are moving away from us so quickly on large scales that their light may never reach us, no matter how long we wait. This creates a gentle but unsettling idea. There are parts of reality that exist, follow physical laws, and contain galaxies, stars, and possibly planets, yet remain forever outside our observational reach. When we imagine what lies beyond this boundary, it is tempting to picture a kind of edge, like the end of a map where unknown territory begins. But in cosmology, there is no reason to believe that the universe changes its nature at the boundary of what we can see. The laws of physics are expected to continue in the same way beyond the horizon. In other words, the unobservable universe is not different from the observable one. It is simply unseen. One of the most important ideas in modern cosmology is that the universe is likely much larger than the observable portion. It could extend far beyond the cosmic horizon, repeating similar structures in different configurations, or it could be so vast that the observable universe is only a tiny region within it. Some models even suggest that the universe may be infinite in spatial extent. In such a case, the observable universe would be just a finite bubble within an endless expanse of space. However, because we cannot receive information from beyond the horizon, all of these possibilities remain open. We can infer, but not directly confirm, what lies beyond. There is also an interesting symmetry hidden in this idea. Every observer in the universe has their own observable region centered on their location. A distant galaxy billions of light years away has its own observable universe, overlapping with ours but extending in different directions. In that sense, there is no single privileged observable universe. There are many overlapping spheres of observation, each defined by its own position in spacetime. This leads to a quiet realization. The universe is not divided into what exists and what is far away. Instead, it is divided into what can be seen from here and what cannot yet be seen from here. Even more subtly, the boundary of observability is not fixed in a simple way. As time passes, new light continues to arrive from regions that were previously too distant. At the same time, the accelerated expansion of space pushes other regions further away, potentially beyond future reach. So the observable universe is not static. It evolves. Now, when we return to the original question, what is the universe expanding into? The idea of the unobservable universe adds another layer. Even if there is a vast region beyond what we can see, that region is still part of the same space-time structure. It is not a separate external space. It is simply more of the same universe, extending beyond our current horizon. So expansion is not about the universe growing into an external emptiness. It is about distances increasing within a structure that may extend far beyond what we can ever observe. This is where the imagination often tries to insert an outside, a surrounding void in which the universe sits like an object. But cosmology does not require such a framework. The universe, as far as current understanding goes, is self-contained in terms of spatial definition. There is no confirmed external stage on which it expands. Instead, the unobservable universe reminds us of something more subtle. The limits of observation are not limits of existence. They are limits of access. And as this idea settles, the universe becomes not smaller because of the horizon, but larger in the imagination, stretching beyond visibility into regions that may forever remain hidden, yet still fully part of the same continuous, expanding fabric of space-time. When we try to imagine the full shape of the universe, the mind usually reaches for familiar categories. Things are either finite, meaning they have an end, or infinite, meaning they continue without limit. But space itself does not always fit neatly into these everyday categories, and cosmology leaves both possibilities open in a way that feels quietly unsettling. The universe could be infinite in extent, or it could be finite but without any edge. Both options avoid the idea of a boundary in the way we usually imagine it. If the universe is infinite, then space simply continues forever in every direction. There is no outer region, no final wall, no last point. In such a universe, expansion does not mean the universe growing into more space. It means that all distances within that infinite structure are increasing over time. Even an infinite universe can expand, because expansion refers to changing distances, not to adding new outer layers. This can feel paradoxical at first. How can something infinite grow larger? But the key is that larger in this context does not mean adding new space outside. It means that the scale of separation between points increases everywhere at once. Infinite space can still stretch because stretching is about geometry, not about edges. Now consider the other possibility, a finite universe that is unbounded. This idea is harder to visualize because it removes the familiar concept of an edge entirely. A helpful analogy, though not a perfect one, is the surface of a sphere. The surface is finite in area, but if you travel in any direction on it, you never encounter a boundary. You simply continue moving along the curved surface. In this analogy, you can never fall off the surface because there is no edge to fall from. Yet the surface still has a finite size. In cosmology, space could behave in a similar way, but in 3 dimensions instead of 2. In a finite but unbounded universe, space would curve back on itself in a higher dimensional sense. If you traveled far enough in one direction, you could eventually return to your starting region, not because space is looping in a simple way like a circle in flat space, but because the geometry itself is closed. In such a universe, expansion would still occur. The distances between points would still increase as space stretches. But even then, there would be no edge being pushed outward into something external. The entire closed structure would simply evolve in scale. Both infinite and finite unbounded models share a crucial feature. Neither requires an outside space. There is no need for a surrounding emptiness into which the universe expands. The universe, in both cases, contains all of space that exists within its definition. This is where the concept of expansion becomes especially subtle. Expansion does not depend on whether the universe has an edge. It depends on how distances between points within the universe change over time. So the question, what is it expanding into, begins to lose its structure in both scenarios. If space is infinite, there is no outside to expand into. If space is finite but unbounded, there is still no outside, because all possible space is already contained within the structure itself. What remains is the idea of scale. The universe can change in scale without changing its fundamental topology. Distances can grow without requiring additional space beyond what already exists. This also connects back to observations. When we measure cosmic expansion, we are not detecting an edge moving outward. We are detecting a uniform change in the distance relationships between galaxies. That change does not reveal a boundary, only a consistent stretching behavior across space. There is also a deep philosophical shift hidden in this. Our intuition is built from life inside finite objects, rooms, planets, and visible horizons. Everything we experience has boundaries, but the universe may not share that feature at all. Its most fundamental property may be relational rather than bounded. In other words, what matters is not where space ends, but how space behaves. And as this idea settles, the universe becomes less like a contained object floating in a larger void, and more like a self-contained structure whose size and shape are defined entirely by internal relationships, with expansion being a change in those relationships rather than movement into anything beyond them. As we go deeper into the nature of space, another idea naturally appears in the imagination. If the universe can curve, stretch, and evolve, then perhaps it is embedded in something larger, higher dimensional space that allows it to bend the way a sheet of paper bends in our hands. This thought comes from a very familiar experience. A flat surface can be curved when it exists inside a higher dimensional environment. A sheet of paper can be folded, bent, or rolled because it sits in 3-dimensional space. So it is tempting to assume that our 3-dimensional universe must also sit inside something even larger. But modern cosmology does not require this assumption. When physicists talk about the curvature of space, they are not necessarily talking about bending into a higher external dimension. They are describing curvature as an internal property of space itself. In this view, space does not need to be embedded in anything else to curve. It curves in relation to itself. To understand this gently, Imagine you are a two-dimensional being living on the surface of a sphere. You have no access to the third dimension outside the surface, yet you can still discover that your space is curved. You might measure triangles whose angles do not add up the way they would in flat geometry. You might notice that parallel lines eventually behave in unexpected ways. All of this would tell you that your universe has curvature, even though you never experience the higher dimension directly. In the same way, our universe can have curvature that is measurable from within, without needing an external space to curve into. This is one of the quiet achievements of general relativity. It describes gravity not as a force acting in a background space, but as the curvature of space-time itself. Mass and energy tell space-time how to curve, and that curvature tells matter how to move. Everything happens within the same self-contained structure. So when we speak about space curving, we are describing relationships between points inside the universe, not the universe bending into an external container. This leads to an important correction of intuition. The idea of a higher dimensional outside is not required by the mathematics of general relativity. It is a helpful visualization tool in some cases, but it is not a necessary part of the theory. There are models in physics that do include higher dimensions, especially in advanced theories like string theory or certain cosmological models. In those frameworks, additional dimensions can play a role in how forces and particles behave. But even in those cases, the existence of an external space is not a settled requirement for explaining cosmic expansion. What we can say with confidence is that curvature is measurable within the universe itself. Light bends around massive objects, time slows in gravitational fields, and the geometry of space changes depending on energy and mass distribution. All of these effects are observed internally, without needing an external reference space. Now, when we return to the idea of expansion, curvature adds another layer of subtlety. The universe can expand while also being curved. Expansion describes how distances change over time, while curvature describes how those distances are arranged spatially at any given moment. These are two different aspects of the same space-time structure. One is dynamic, the other is geometric. So the universe is not simply a flat, stretching grid. It can be curved, warped, and uneven in its geometry, while still expanding uniformly on the largest scales. This leads to another quiet realization. Even if the universe were embedded in a higher dimensional space, we would have no direct observational access to that embedding. All measurements would still come from within the universe itself. That means the concept of an external space remains speculative rather than necessary. And as this settles, the imagination begins to shift again. Instead of picturing the universe as something bending into a larger emptiness, it becomes more natural to see it as a complete structure whose curvature is defined internally, whose expansion is intrinsic, and whose geometry does not depend on anything beyond itself. There is a point in this journey where the mind naturally tries to step back one more level, as if it could leave the universe behind and look at it from an external vantage point. From that imagined position, it becomes tempting to ask what lies outside space-time itself, as though space-time were an object sitting in a larger arena. This is one of the most intuitive ideas in human thinking, because almost everything we experience is contained within something else. Objects sit in rooms, rooms sit in buildings, buildings sit on land, and land sits on a planet. The mind builds a chain of containment, and it tries to extend that chain all the way up to the universe itself. But space-time does not behave like the objects inside it. Space-time is not a thing located somewhere. It is the framework that defines what somewhere means in the first place. It is the structure that gives meaning to distance, direction, and duration. Because of that, asking what lies outside space-time may be similar to asking what exists north of the North Pole. The question uses a structure that stops being defined at the limit it tries to extend beyond. In modern physics, space-time is treated as a self-contained system. It is described mathematically not as a substance inside a container, but as a set of relationships between events. An event is simply something that happens at a place in time, and space-time describes how those events are connected. This means that outside space-time does not have a clear operational meaning. There is no coordinate system beyond space-time in which we can place additional physical objects or regions, at least not within the standard framework of general relativity and cosmology. Still, the idea of an outside persists in imagination because it feels like something must be holding the universe in place. But this feeling comes from everyday experience with bounded systems. A table exists in a room, and the room exists in a building, so it feels natural to assume that the universe must exist in something larger as well. However, space-time is not one object among others. It is the total system within which all objects and events are defined. There is no known observational evidence that requires an external embedding space. When we describe the universe expanding, we are describing changes within space-time itself. The expansion is not motion into an external volume. It is the internal evolution of the distances that space-time defines. Even the concept of outside relies on space-time structure. Outside implies a spatial relationship, a separation, a direction away from a boundary. But if space-time defines all spatial relationships, then the notion of outside cannot be constructed within the same framework. This does not mean that physics claims to know everything about reality. It only means that within the current models that successfully describe cosmic expansion, an external space-time is not required. There are speculative ideas in theoretical physics that explore extensions of space-time, such as higher dimensional frameworks or multiverse scenarios. In some of these, our universe might be one region embedded in a larger structure. But these ideas remain outside direct observational confirmation, and they are not needed to explain the expansion we measure. What we observe instead is internally consistent. Galaxies recede, light stretches, space evolves, and all of it can be described without referencing anything beyond the universe itself. So the outside of space-time becomes less like a hidden region waiting to be discovered, and more like a concept that dissolves when its assumptions are examined closely. And as this realization settles, the universe becomes not an object floating in something larger, but a complete framework where even the idea of an external backdrop loses its meaning, because every notion of space and separation already belongs entirely to the structure we are trying to describe. At this point in the journey, once the idea of an outside begins to fade, another possibility sometimes appears in modern cosmological thinking, the idea that our universe might not be the only one. Instead, there could be many universes, existing in a larger structure often called a multiverse. This concept is not a single idea, but a family of different models, each arising from different areas of theoretical physics. Some come from inflation theory, some from quantum mechanics interpretations, and some from attempts to unify fundamental forces. What they share is the suggestion that what we call the universe might be only one region within a much larger reality. In some inflationary models, the early universe undergoes a rapid expansion phase, and this process may not happen just once. Instead, it could continue in different regions, creating separate bubble universes, each with its own local conditions. In this picture, our observable universe would be one bubble among potentially many others, each separated by regions we can never access. These bubble universes would not necessarily be expanding into a shared external space in the usual sense. Rather, each bubble would be a self-contained region of space-time with its own internal expansion history. The separation between them would be so extreme, and the expansion of space so dominant, that communication between bubbles would be effectively impossible. Another form of multiverse idea comes from quantum physics interpretations. In some interpretations, every possible outcome of quantum events may branch into separate histories. In this view, different universes represent different realized outcomes of quantum processes, existing in a vast branching structure of possibilities. There are also higher dimensional models where our universe could be a kind of membrane, sometimes called a brain, existing within a higher dimensional space. In these models, other brains could exist parallel to ours, forming a kind of layered structure of universes. However, it is important to understand what these ideas do and do not claim. They do not directly change the explanation of cosmic expansion that we observe. The expansion of galaxies, the redshift of light, and the large-scale structure of space all remain described by the same internal physics within our universe. The multiverse, if it exists, would be beyond our observational horizon. By definition, it refers to regions or structures that cannot be directly accessed or measured using light or any known signal. This makes the multiverse concept both fascinating and difficult. It extends the imagination beyond the observable, but it also pushes against the limits of empirical science. In most cases, it remains a theoretical extension rather than an established fact. Still, it naturally connects to the question of what the universe is expanding into. If multiple universes exist, one might imagine expansion happening within a larger framework that contains many such regions. But even in these models, the expansion we observe inside our universe is still described as internal stretching of spacetime, not movement into a shared external emptiness. Each universe, if it exists, would have its own internal geometry and its own expansion behavior. They would not necessarily share a common spatial background. So even the multiverse does not clearly restore the idea of a single external container. Instead, it replaces one universe with many self-contained systems, each with its own space-time structure. This leads to a subtle shift in perspective. The question, what is the universe expanding into, does not become simpler in a multiverse scenario. It becomes layered. One level of expansion occurs within our universe, and any higher structure, if it exists, remains speculative and inaccessible. What remains consistent across all these models is the internal nature of expansion. Whether the universe is alone or part of a larger ensemble, the expansion we measure is always a change in the relationships between points within spacetime. And as this idea settles, the multiverse becomes less like an answer to the outside question and more like a collection of possibilities that still preserve the central insight. That expansion does not require an external space, only an evolving structure of spacetime itself. If we move further back in time, beyond the familiar picture of galaxies and cosmic structure, we reach a stage where the universe behaves in a far more extreme and rapid way. This is the era of cosmic inflation, a short but powerful phase in the very early universe where expansion is thought to have occurred at an astonishing rate. Inflation is not just a gradual stretching of space. It is a period where space itself is believed to have expanded exponentially in an extremely small fraction of a second. During this time, the universe may have grown from something far smaller than an atom to a size much larger than what we can easily imagine, all in an almost instantaneous moment on cosmic timescales. This idea helps explain several features of the universe we observe today. One of them is the remarkable uniformity of the cosmic microwave background, the faint radiation that fills the universe in all directions. Inflation provides a way to understand how distant regions of space, which would otherwise have been too far apart to share information, could have once been close enough to reach thermal balance before being rapidly separated. Another important consequence of inflation is the smoothing of large-scale geometry. Even if the early universe had small irregularities or curvature, rapid expansion would have stretched space so much that, on large scales, the universe would appear very flat and uniform to observers like us. But inflation also deepens the question we have been exploring. During this phase, space itself is not just expanding in a gentle way. It is undergoing a dramatic transformation in scale. This makes the idea of Into what is it expanding? Even less intuitive, because the expansion is happening so rapidly and uniformly that no external reference frame is needed or even defined within the model. In inflationary theory, the driving mechanism is often described as a high-energy field that filled space in the early universe. This field had a form of energy associated with the vacuum itself, and this energy caused space-time to expand extremely quickly. As the inflationary phase ended, that energy was converted into particles and radiation, filling the universe with the matter and energy that would later form galaxies and stars. What is important here is that inflation does not require space to be embedded in anything else. The expansion is still an internal property of space-time. It is driven by the energy content within the universe, not by any external influence. This is where intuition can become stretched. We are used to thinking of expansion as something pushed from the outside or driven into empty surroundings. But in inflation, the entire region of space is changing scale at once. Every point participates in the expansion simultaneously. There is no edge leading the way, no frontier moving outward into a surrounding void. Instead, the universe behaves like a system whose internal rules cause its size to increase rapidly. The change is global, not directional. After inflation ends, the universe transitions into a slower expansion phase, the one we are still experiencing today. The dramatic early growth leaves behind a kind of imprint in the structure of the universe, influencing the distribution of matter and the patterns we observe in cosmic background radiation. Inflation also helps explain why the universe appears so uniform on large scales. Regions that are now extremely far apart were once close enough to share conditions before being separated by rapid expansion. This gives a natural explanation for the smoothness we observe across the sky. Yet even with this powerful framework, the deeper question remains unchanged. Inflation describes how space expanded, but it does not introduce an external space into which expansion occurs. It remains a description of internal dynamics, not movement into an outside environment. So even at the earliest known stage of cosmic evolution, the universe does not appear to require an into what. Instead, it behaves as a self-evolving geometry whose scale changes according to its internal energy and structure. And as this idea settles, inflation becomes not a doorway to an outside realm, but a reminder that the most extreme expansion we can describe still takes place entirely within the universe itself, without the need for anything beyond it. After the early universe settled from its intense inflationary phase, expansion did not stop. It slowed, changed character, and continued in a more gradual way. But in the late 20th century, observations revealed something unexpected. The expansion of the universe is not slowing down under gravity. It is accelerating. This discovery came from studying extremely distant supernovae, which act as standard candles, objects whose intrinsic brightness is known well enough to measure distances across the universe. When astronomers compared their brightness with their redshift, they found that distant galaxies were farther away than expected. This implied that the expansion of space had been slower in the past and has been speeding up over time. To explain this acceleration, cosmologists introduced the idea of dark energy, a name given to whatever is driving this effect. Dark energy is not directly observed like matter or radiation. Instead, it is inferred from its influence on the large-scale behavior of space-time. One of the simplest ways to describe dark energy is as a property of space itself. Even empty space, with no matter or radiation, may still contain energy associated with its structure. This energy would not dilute as the universe expands. Instead, it would remain constant per unit volume, causing the total amount of energy to increase as space itself grows. This creates a very unusual effect. As the universe expands, more space appears. And if that space carries a form of energy, inherent to its nature. Then the total energy driving expansion increases as well. This leads to accelerated expansion over time. From our perspective inside the universe, this acceleration means that distant galaxies are not just moving away, but doing so at an increasing rate over extremely long timescales. Regions of space that are not gravitationally bound will recede from each other faster and faster. This behavior strengthens the sense of separation on cosmic scales. Distant parts of the universe become increasingly isolated as the space between them stretches more rapidly. Yet even this accelerating expansion does not introduce an external space. Dark energy does not push the universe outward into anything. It acts within space-time itself, influencing how space-time evolves. This is an important point. The acceleration is not caused by a force acting from outside the universe. It is a property of the universe's internal structure. In mathematical terms, it appears as a term in the equations of general relativity that affects the large-scale dynamics of space-time. One of the simplest interpretations is that space has an intrinsic tendency to expand when not strongly constrained by matter. In regions where matter is sparse, this effect becomes dominant, allowing expansion to accelerate. As a result, the large-scale fate of the universe may be shaped by dark energy. If it remains constant, expansion will continue accelerating indefinitely. Over extremely long periods of time, galaxies outside local clusters will drift beyond each other's observable horizons, leaving isolated regions of gravitationally bound systems. In such a scenario, the universe becomes increasingly empty on large scales, not because matter disappears, but because space between structures continues to grow. This leads to another subtle reflection. Even as expansion accelerates, it still does not require an outside. The universe does not need a surrounding void to stretch into. The acceleration is a change in the rate at which internal distances increase. So dark energy deepens the original question rather than resolving it. It shows that expansion is not a simple leftover from the early universe, but an ongoing feature of space-time itself. And as this idea settles, the universe appears even more self-contained, where the very emptiness of space is not truly empty, but active in its own quiet way, shaping the long-term evolution of everything within it, without ever needing anything beyond its own boundaries. When we zoom out far enough from individual galaxies, a different kind of pattern begins to emerge, one that is not random, but also not smooth in the way a simple gas might fill space. Instead, the universe reveals a vast and delicate architecture, often described as the cosmic web. This structure is made of immense filaments of galaxies, stretching across hundreds of millions of light years, connected at dense nodes where galaxy clusters form, and separated by enormous empty regions known as voids. It looks less like a uniform distribution, and more like a three-dimensional network suspended across space. What is important is that this structure did not exist in the early universe. It formed gradually over billions of years as a result of the interplay between gravity and expansion. In the early universe, matter was distributed almost uniformly, with only tiny fluctuations in density. Over time, gravity amplified these small differences. Regions that were slightly denser attracted more matter, growing gradually into galaxies and clusters. Meanwhile, less dense regions became increasingly empty as matter was pulled away. At the same time, the expansion of space continued to stretch the universe on large scales. This meant that while gravity was pulling matter together locally, expansion was increasing the separation between structures that were not strongly bound. The result is the cosmic web, a structure shaped by both attraction and expansion, working together over immense timescales. Filaments form where gravity has successfully gathered matter into long connected structures. Voids form where expansion and lack of matter have allowed space to grow relatively empty. Nodes form where filaments intersect, creating dense clusters of galaxies. This structure tells us something very important about expansion itself. It shows that expansion is not uniform in its effects on matter distribution. It operates most strongly where gravity is weakest, allowing large empty regions to grow, while leaving dense regions relatively intact. So the universe is not simply expanding like an evenly stretched balloon in all respects. It is expanding in a way that interacts with existing structures, enhancing emptiness in some regions while preserving complexity in others. This brings us closer to understanding what expansion really means. It is not just a global increase in distance. It is a process that reshapes the relationship between matter and space over time. Even within this cosmic web, there is no sign of an external direction or edge. The filaments do not point outward toward anything. They exist within the same expanding geometry, and their arrangement reflects internal dynamics rather than movement toward an outside region. Another important feature of a large-scale structure is that it supports the idea of a universe that is homogeneous and isotropic at the largest scales. Even though locally the universe looks extremely structured, when averaged over vast distances, it becomes statistically uniform. This means that no large region of space is fundamentally different from another in terms of overall properties. This uniformity is one of the reasons cosmologists can model the universe using simple large-scale equations, even though its small-scale structure is highly complex. The cosmic web also helps illustrate why expansion does not break bound structures apart. Within galaxies and clusters, gravitational forces are strong enough to hold matter together against the stretching of space. But between these structures where gravity is weak, expansion dominates and increases separation over time. So the universe behaves like a layered system, where local structure is preserved while global separation increases. And as this picture forms, the universe begins to feel less like a simple expanding volume, and more like a slowly evolving network, where space, matter, and gravity continuously reshape each other, without ever requiring a boundary or external stage on which this transformation occurs. When people first hear that the universe is expanding, a very natural worry appears. If space itself is stretching, then why do we not feel it? Why are atoms not pulled apart? Why do planets remain stable? And why does everything around us seem unchanged? The answer lies in scale, and in the strength of the forces that hold structures together. Expansion of the universe is extremely important on cosmic distances, but it becomes almost irrelevant when we move to smaller and smaller systems. The reason is that different forces dominate at different scales, and expansion only becomes noticeable where those forces are weak. Inside atoms, the electromagnetic force holds electrons and nuclei together with extraordinary strength. This force is many orders of magnitude stronger than the effects of cosmic expansion at that scale. As a result, atoms do not expand with the universe. Their internal structure remains stable. Inside planets, gravity binds matter tightly. The Earth, for example, is held together by gravitational attraction, strong enough to completely overwhelm any effect from the slow stretching of space. The same is true for the Moon, for the Sun, and for the entire solar system. Even at the scale of galaxies, gravity continues to dominate. Stars orbit the center of the Milky Way because the gravitational field of the galaxy is strong enough to resist the expansion of space within that region. It is only when we move to extremely large distances, between galaxies that are not gravitationally bound, that expansion becomes the dominant effect. In those regions, space itself stretches in a way that increases separation over time. This layered behavior creates a very important picture of the universe. It is not uniformly expanding in a way that affects everything equally. Instead, it is expanding in a way that becomes significant only where internal forces are weak. So from the perspective of everyday life, expansion is invisible. It does not pull apart chairs, buildings, or human bodies, because those systems are bound by forces far stronger than the gentle stretching of cosmic distances. This is why humans do not experience expansion directly. We are made of atoms that are held together by strong interactions. Our bodies are part of a stable local system that is effectively isolated from the large-scale stretching of the universe. Yet even though we do not feel it, we are still part of the expanding cosmos. We exist within space-time. And on very large scales, our location participates in the overall growth of distances between distant structures. This creates a quiet duality. On one hand, we live in a stable, bounded environment where everything feels fixed and familiar. On the other hand, we are embedded in a universe whose large-scale structure is slowly evolving, with galaxies drifting apart over billions of years. This difference between local stability and cosmic change is one of the reasons the universe feels both familiar and infinite at the same time. There is also a deeper insight here. Expansion is not a force that acts uniformly on everything. It is a feature of space-time that becomes visible only when nothing else dominates. Where structure is strong, action is hidden. Where structure is weak, expansion becomes apparent. So in a sense, the universe is always expanding, but we only notice it in the spaces where nothing strongly resists it. As this idea settles, the scale of the universe becomes more layered in the mind. At the smallest level, atoms remain unchanged. At the human scale, everything feels stable and continuous. At the scale of galaxies, structure holds together. And at the largest scale of all, space itself slowly stretches, carrying distant regions further apart over time. And through all of this, the same underlying principle quietly remains. Expansion is not something that breaks the universe apart from the inside, but a gradual change in the geometry that connects everything together, acting only where nothing else is strong enough to resist it. When we look at the universe on its largest scales, one of the natural questions that follows is whether this expansion is permanent, or whether it could one day slow down, stop, or even reverse. This question is not just about the present behavior of space, but about the long-term fate of everything within it. To understand this, we need to return to what drives expansion in the first place. The large-scale evolution of the universe is governed by its total energy content, including matter, radiation, and dark energy. Each of these components influences the geometry of space-time in different ways. Matter, both visible and dark, tends to slow expansion over time. Its gravitational attraction pulls structures together and resists the separation of space. In the early universe, when matter density was higher, this effect was more significant, and expansion was decelerating compared to the initial rapid phases. Radiation also contributes in a similar way, though its influence decreases as the universe expands and radiation becomes more diluted. Dark energy, on the other hand, behaves differently. It does not dilute in the same way as matter or radiation. Instead, its influence remains roughly constant per unit of space. This means that as the universe expands and more space is created, the total effect of dark energy increases, allowing expansion to accelerate. So, the long-term behavior of the universe depends on the balance between these components. If matter had dominated completely, it is theoretically possible that expansion could have slowed enough to eventually stop. In some hypothetical scenarios, gravity could overcome expansion on the largest scales, leading to a contraction phase known as a big crunch, where the universe would begin to collapse back toward a denser state. However, current observations suggest that dark energy is dominant in the present universe. This makes continued expansion, and even accelerated expansion, the most likely long-term outcome under known physics. If dark energy remains constant over time, then expansion will not stop. It will continue indefinitely, with galaxies outside local gravitational systems drifting further apart as space itself keeps stretching. If dark energy were to change in strength or nature, different outcomes could be possible. Some speculative models suggest scenarios where expansion slows, stabilizes, or even reverses. But there is currently no strong observational evidence for such changes. What is important to understand is that expansion is not a one-time event that happened in the past. It is an ongoing process. The universe is not expanding into something and then stopping. It is continuously evolving according to its internal energy balance. So when we ask whether expansion could stop, we are really asking whether the internal conditions of space-time could change in a way that alters its large-scale behavior. That is a question about the future evolution of energy, not about an external boundary or force. Even in scenarios where expansion slows or reverses, the concept of into what does not become simpler. A contracting universe would still not require an external space to collapse into. It would still be a self-contained system where distances between points change according to internal dynamics. So whether the universe expands forever or eventually changes direction, the key idea remains the same. The universe does not need an outside in order to evolve. Its behavior is defined entirely by what happens within spacetime itself. And as this idea settles, the long-term future of the cosmos begins to feel less like a journey toward an external destination, and more like a continuing shift in the structure of everything that already exists, unfolding according to rules that do not require anything beyond the universe to operate. When we extend our view far beyond the present moment, beyond even the lifespan of galaxies and stars, cosmology begins to describe a future that is quiet, vast, and increasingly empty in structure. This is often called the heat death of the universe, though the phrase sounds more dramatic than the reality it describes. It does not refer to destruction in a violent sense. Instead, it refers to a gradual approach toward equilibrium, where usable energy differences fade away and the universe becomes increasingly uniform. To understand this, it helps to return to expansion. As space expands, galaxies outside gravitationally bound systems move farther apart. Over extremely long timescales, star formation will slow as galaxies exhaust their gas reservoirs. Existing stars will age and eventually die, leaving behind remnants like white dwarfs, neutron stars, and black holes. As expansion continues, even the distances between galaxy clusters will grow so large that they become isolated islands in an increasingly empty cosmic ocean. Each gravitationally bound system will become more and more separated from others as space stretches between them. In this scenario, the universe does not stop existing, but it becomes less structured. Energy becomes more evenly distributed. Temperature differences decrease. Processes that rely on gradients, such as star formation or large-scale thermodynamic activity, gradually fade. This is where the term heat death comes from. It refers to a state in which the universe reaches maximum entropy, meaning the energy is spread out in such a way that no large-scale work can be extracted from it anymore. Even in this distant future, expansion does not require an external space. The universe does not spread into emptiness outside itself. It simply continues evolving internally, with distances increasing and structures becoming more isolated. One of the most striking aspects of this long-term scenario is the changing nature of the night sky. In the far future, observers within a galaxy might look up and see a sky dominated almost entirely by their own local stars. Distant galaxies would have long since slipped beyond the observable horizon due to expansion. Eventually, even those local stars would die, leaving behind faint remnants scattered across vast distances over incomprehensibly long timescales. Even black holes are expected to slowly lose energy through processes like Hawking radiation, eventually evaporating into faint radiation. After that, only extremely dilute particles and low-energy photons may remain, spread across an ever-expanding space. Yet even in this scenario, space-time itself continues to exist. Expansion, if driven by dark energy as current models suggest, would not stop. It would continue shaping the geometry of the universe, increasing distances between remaining particles over time. This leads to a very subtle reflection. The heat death scenario is not an ending in the sense of a final boundary. It is a transformation into a state where structure and change become extremely rare. The universe does not reach an edge or collapse into an outside. It continues internally, but in a form that is increasingly uniform and inactive. From within such a future, the concept of expansion would still be valid, but it would describe a much emptier and quieter cosmos. Distances would still increase on the largest scales, but there would be fewer structures left to observe that change. So even the ultimate long-term fate of the universe does not introduce an into what. It remains a story of internal evolution, where space-time changes its scale and structure without reference to anything beyond itself. And as this idea settles, the universe feels less like a system moving toward an external destination, and more like a slowly unfolding silence, where structure fades, distance grows, and the geometry of everything continues to evolve within itself, without ever needing an outside to complete the story. Even though the standard model of cosmology describes a universe that expands according to general relativity and dark energy, science also explores other possible descriptions of reality. These alternate cosmological models do not replace what we observe, but they attempt to interpret the same observations in different ways, or extend them into regimes where our current understanding may be incomplete. One class of alternatives modifies the nature of dark energy. In the standard picture, dark energy behaves like a constant property of space, but in some models, it can vary over time or interact with matter in more complex ways. If this were true, the long-term expansion history of the universe could be different from what we currently expect. Expansion might slow more significantly, remain steady, or even change behavior in unexpected ways depending on how this component evolves. Another category involves modifications to gravity itself. Instead of assuming that general relativity is complete on the largest scales, some theories propose small changes to how gravity behaves over cosmic distances. These changes could alter how expansion accelerates, or how structures form over time, without requiring dark energy in its simplest form. There are also cyclic models, where the universe does not expand forever in a single direction of time, but instead goes through repeating phases. In such scenarios, expansion could eventually slow, reverse, and lead to a contraction phase, followed by another expansion. The universe would not have a single beginning and end, but a series of transitions between different states. Some more speculative ideas suggest that what we perceive as expansion might be part of a deeper structure where space-time itself emerges from more fundamental components. In these approaches, space and time are not primary, but arise from underlying quantum or informational systems. Expansion, in this view, would be an emergent behavior of deeper dynamics rather than a fundamental process. There are also models that explore anisotropic or non-uniform universes on very large scales. While observations strongly suggest large-scale uniformity, these models examine what would happen if slight directional differences existed in the structure or expansion rate of space. Even in these cases, the concept of expansion remains internal to spacetime, not requiring an external environment. What connects all of these alternate models is that none of them directly reintroduce a clear physical outside into which the universe expands. Even when the mechanisms of expansion differ, the underlying description remains rooted in changes within spacetime itself, or in structures that define spacetime. This is an important point. Across different theoretical approaches, the universe is still treated as a self-contained system in terms of observable geometry. Whether expansion is driven by dark energy, modified gravity, cyclic dynamics, or deeper quantum processes, it is always described through internal relationships rather than motion into an external space. These models are valuable because they test the boundaries of our understanding. They help scientists ask what parts of our current picture are firmly supported by observation and what parts might change as new data becomes available. Cosmology is still an active field, and the deepest questions about the nature of space and time are not fully settled. However, despite these variations, the core observational fact remains stable. Galaxies are receding on large scales, light is redshifted, and space-time is evolving. Any successful model must reproduce these features. So alternate cosmologies do not eliminate expansion, they reinterpret it. And as this idea settles, it becomes clear that even when we explore different possible versions of the universe, the concept of expansion consistently remains an internal property of whatever structure describes space-time, rather than an emotion into something external waiting beyond it. As we approach the edges of what physics can describe with confidence, the question of what the universe is expanding into begins to shift away from pure geometry and into something more abstract. It starts touching the idea of nothingness itself, and what it even means for something to exist without a surrounding space. In everyday language, nothingness often means empty space, a dark void without matter or light. But in cosmology, even empty space is not truly nothing. Space has structure, it has geometry, it can stretch, curve, and carry energy in subtle ways. So the emptiness of the universe is already a kind of physical entity with properties. This creates a deeper question. If even an empty space is something, then what would true nothingness be? Not empty space, but the absence of space, absence of time, absence of any structure that could define distance or direction. At this point, language begins to struggle because most words we use assume a background of space-time. To say where or outside already assumes a spatial framework. Without space-time, those concepts lose meaning. Some philosophical interpretations suggest that asking what lies outside the universe is similar to asking what lies outside existence itself. If the universe includes all space-time, then outside may not be a location that can be defined, but rather a limit of conceptual language. Other interpretations take a different approach. They suggest that what we call nothingness may still have structure in ways we do not yet understand. In quantum physics, even the vacuum is not truly empty. It contains fluctuations, temporary particles, and fields that are never fully at rest. This has led some thinkers to propose that what we call nothing is actually a very active state of potential. In this view, the boundary between something and nothing becomes less clear. The universe may not have emerged from absolute nothingness, but from a state that already had physical laws or underlying structure. There are also philosophical perspectives that treat the universe as a necessary structure, something that cannot meaningfully be said to exist within or outside anything else. In such views, existence is not a thing located in space, but the totality of all possible relations and experiences. Across all these interpretations, one theme repeats quietly: the idea of an external emptiness into which the universe expands becomes harder to define with precision. Either nothingness is not a physical space at all, or it already contains some form of structure that makes it more than nothing. So the question transforms. Instead of asking what the universe is expanding into, we begin to ask what we mean by into in the first place. The word depends on spatial relationships, and spatial relationships are defined within the universe itself. This does not provide a final answer, but it reshapes the question. It suggests that the feeling of an outside may come from the way human intuition builds images from everyday experience, rather than from something required by physical theory. And as this reflection settles, nothingness becomes less like a surrounding void waiting beyond the universe, and more like a limit of language and imagination, where our usual ways of describing space gently stop being applicable, leaving only the universe itself, complete within its own definition of existence. At this stage of the journey, the question of what the universe is expanding into begins to sit right at the boundary between what physics can describe clearly and what it can only approach indirectly. This is where science becomes both powerful and limited at the same time, not because it is failing, but because it is working with the structure of reality as it is accessible from within. Science is extremely effective at describing how expansion behaves. It can measure how fast galaxies recede, how light is redshifted, how the cosmic microwave background carries information from the early universe, and how space-time evolves under the influence of matter and dark energy. These are all grounded in observation, mathematics, and repeated verification. What science does not currently provide is a direct description of anything outside space-time, because all measurements, all signals, and all physical theories are defined within space-time itself. Every experiment is performed inside the universe, and every result is interpreted using rules that assume space-time as the fundamental stage. This creates a natural boundary. If something cannot interact with space-time, or cannot send information into it, then it cannot be tested using current scientific methods. That does not mean it is impossible or meaningless, but it does mean it lies beyond the reach of empirical confirmation for now. The question of what the universe is expanding into often falls into this category. It assumes a surrounding structure that may not be part of the physical model at all. Science can describe expansion in great detail, but it does so entirely in terms of internal geometry, not external environment. At the same time, science remains open to revision. History shows that our understanding of space, time, and the universe has changed dramatically over time. What once seemed absolute, such as the idea of a static universe, was later replaced by the discovery of expansion. So the current limits of knowledge are not fixed barriers, but current boundaries of understanding. There are also theoretical ideas that attempt to go beyond these limits. Some approaches in quantum gravity suggest that space-time itself may emerge from more fundamental structures. In such cases, what we call expansion might be a large-scale effect of deeper processes. But even in these frameworks, the concept of an external spatial container is not necessarily introduced in a simple way. Instead, the notion of space itself becomes something derived rather than fundamental. So science can answer many how questions about expansion, how it changes over time, how it affects light, how it shapes galaxies, and how it behaves under different energy conditions. But what is it expanding into question often shifts into a different category, where the meaning of the words themselves becomes part of the problem. This is not a failure of science. It is a reflection of how deeply the question depends on intuition. Human experience is built inside space, so it naturally assumes space must exist inside something else. But physics, as currently formulated, does not require that assumption. So we arrive at a careful position. Science can describe the expansion of the universe with increasing precision, but it does not currently provide evidence for an external spatial region into which expansion occurs. At the same time, it does not claim to have a final picture of reality beyond space-time either. What remains is a structured silence at the edge of knowledge, where models work beautifully within their domain, but do not extend in a straightforward way to questions that assume something beyond that domain. And as this understanding settles, the universe feels less like a question with a missing piece, and more like a complete descriptive framework whose boundaries are defined by observation itself, leaving certain ideas not as answers waiting to be found, but as concepts that may simply lie outside the language we currently have for describing reality.